Yeah. If you remember, there was the first question that we considered was the Atwood's machine, isn't it? The Atwood machine is basically a pulley, and there are two masses which are suspended by means of a thread, and that thread is effectively passing over. That was the Atwood's machine. It is called Atwood's machine. It's technically not a very complicated machine, actually, just a simple pulley. Actually, early on, this was being historically rather, it was utilized to measure the acceleration to gravity, this particular setup, and that is why it is still a bit of having some significance. Basically, the method relies on measuring the kind of acceleration of the falling blocks, which can be used by marking the the background of this moving bodies and finding the time taken by the body to travel a certain amount of distance. In that case, the acceleration could be figured out, and once the acceleration is obtained, because we know the masses and we know the acceleration relation with the gravity, so we can obtain the gravity as well. Acceleration to gravity can be figured out this way. Anyway, so if we remember in this, if you are not yet seen, what we can do over here is, in this case is that we could obtain the acceleration. I already obtained this, but still, the main idea in this case is to draw the free body diagram of two blocks and write down the Newton's laws. First of all, we notice that we usually assume in this case that the thread is going to be not extensible. It cannot be stretched actually. So it is something which is again an idealization, because real threads are up to some degree always stretchable actually a bit. So in this case, once we write down the FBD and draw the, write down the equations for the Newton's laws, it doesn't matter hardly which one is heavy, which is lighter. We end up getting finally there's other thing of this another thing. What is it? This another aspect or another thing that I would like to consider over here. The question is, why is the thread tension taken to be same in this case? In this case, the thread tension, we are assuming that same on both the sides. That is usually always the case as long as the thread doesn't have some mass. If the thread does have some mass, then this can't be true. Okay, but if the thread is massless, or at least negligible mass is there, and it passes over some surface which doesn't have any friction. Even in this case, if there was some friction, then the tension on two sides won't be same actually. But because the entire surface is frictionless, then we can assume the thread tension to be same throughout the thread actually. Okay, that is one thing which happens with thread tension. M1, what is the meaning of M1? Yes, M1, it will be M1G. So in this case, by writing the Newton's laws and solving the equations, rather, I can just write down the equation again, just in a very short while. The point in this case is that we can assume that, okay, there's an acceleration this way, and this is my assumption actually. This is technically unknown in which direction the system is going to accelerate, because we do not know yet the numerical value of the masses. However, we can always start by some assumption. And just remember that this A that I have written down is not the acceleration actually, magnitude wise, but the component of acceleration in the downward direction, which implies this A is an algebraic quantity. It can be positive, it can be negative as well. So in that case, this must be the acceleration A itself. And accordingly, we write down the equation in the reference direction, which is going to be downwards. So I have, these are the second law. That equation will, that body will give us this equation. Normally, we notice that the number of unknowns and number of equations must be, well, I'm assuming Abhiprata, but it's not mandatory. As I said already, M1, this A is technically not the acceleration itself, but the component of the acceleration. It implies a scalar quantity, an algebraic quantity. It can be plus or minus. So I have assumed this to be this way. That M1 is down, but accelerating down, but might not be mandatory. Okay. And I just add these two up, a simple matter. If I add it up, I end up getting M1 minus M2G equal to M1 plus M2 into A. And that gives us the acceleration of this Atwood machine that we find out as m1 minus m2 by m1 plus m2 into g. That becomes the acceleration for the Atwood machine, which effectively is related to the two masses, the difference in numerator sum in the denominator. Now, so you see that if I was able to measure the masses, in that case I could know the acceleration. Conversely, if the accelerations can be measured and the masses of the blocks can be measured as well, then we can figure out the acceleration due to gravity over it, which is what was the original purpose of this device was actually. Fine. Anyway, let us take a slight modification over there. In this case, Asha, by the way, people again who haven't seen it, you see that it can be by using this acceleration, I can just put this in any one of the equation and I can solve for the thread tension. Okay, it turns out the thread tension, that is this T over there, it turns out to be twice m1 m2 by m1 plus m2 into g. That is the thread tension turns out to be. And as a result of which, because this pulley is supposed to be massless, net force has to be 0. It is being pulled downwards by these two tensions. So the force from the support must balance both the tensions over there. And therefore, if I look at the force which the support exerts on the ceiling over here, then that F turns out to be 4 times m1 m2 by m1 plus m2 into g. That's what we have. This is a very useful thing, by the way. Therefore, what it turns out is that if I, for example, replace the entire Atwood machine by a single point mass, whose mass is 4 m1 m2 by m1 plus m2, I'm going to say that this entire setup is equivalent. Therefore, this entire thing is therefore equivalent to just a single point mass suspended from the ceiling by means of this thread, but the mass must be 4 m1 m2 by m1 plus m2. Okay, so if I replace the entire Atwood machine by just a block or single point mass whose mass is 4 m1 m2 by m1 plus m2, that in this case will make no difference to the ceiling actually. From the ceiling as such, you see from the above, the ceiling does not know what is suspended below. What it can just sense is the force which the rope exerts on the ceiling. So as long as that force is the same, it hardly matters what is below or what is actually suspended. So in many cases, it is of great importance or great usefulness actually to simply replace the Atwood machine with a point mass, and that is equal to this. This can be thought of as therefore an equivalent mass of the Atwood machine, pretty much like the equivalent resistance of the resistance that we have or we might have calculated in class 10. In similar fashion, in this case, we can, in many instances, replace the Atwood machine by a single point mass or single block whose mass is equal to that much. Okay, you remember this one, which I'll be using this a bit later on. Okay.